Let's start. I will skip here the company introduction because Putri already introduced us so nicely. Just a quick look here on where Seele is all over the world, especially here in Asia. So we have a branch in India, we have a company in Thailand, one in Malaysia, company in Singapore, this is where I am, and another branch in Australia, and a company running North Asia in Hong Kong. What we are doing, we are having a very intensive or great R&D team there, mainly in Germany. We are doing engineering and design, of course, project management and QM, testing, manufacturing, and logistics and installation. Most of our project management is run by our headquarters for the projects here in Southeast Asia, especially for the more complex projects. For the more simple projects, we do it directly here in Singapore. What kind of technologies are we using? Steel and glass constructions, all glass designs. Here on the right-hand side top, you see the apple of all mothers, mother of all Apple stores in Fifth Avenue in New York, a full glass construction. We are doing unitized facades. This here is the European Central Bank. And membrane construction. Here in Southeast Asia, we are mainly concentrating on the steel and glass constructions and on the all glass designs. So let's start with the introduction of the 33rd Street Penn Station entrance in New York. Here you have a view from the inside to the top. You can see it's a cable truss, a cable net facade with nodal points and scissor fixing. We will come to that. Here some impressions from the outside. On the right-hand side, an impression from the installation itself. So the whole construction consists of 105 tons of steel construction, 277 square meters of cable net with glasses obviously on top, 13-meter high and 139 double curved glazed panels. 13-meter high certainly doesn't sound that big, but you will see how massive that construction in reality is then. So here you have an overview over the construction itself, the steel components here. Let's start on the left top, it's the crown. Then we have the two components we call hockey sticks, to obvious reason coming down. The hockey sticks are connected with a crossbeam, and on the bottom we have a U-shaped steel construction we call horseshoe. The whole thing is then equipped with a cable net that you can see here. Can you actually see my mouse moving?
Yes, I guess.
You see the mouse?
Yeah,
okay.
yes, we can. Yes.
Wonderful, wonderful. And then on top of the cable net, we have the three-dimensionally shaped glass hull of the whole construction. All of the glasses are double curved, meaning not only curved in one direction, but in two directions at the same time, similar to a horse saddle. Here we have some quick impressions of our steel fabrication in Seele Pilsen. That's our Seele Group internal steel fabrication workshop there. It's a real high-end workshop that is currently doing the most stunning and most precise architectural steel works all over the world. Here you see now, for example, a spandrel panel, which is below the horseshoe later on the left-hand side. It's a cladding panel, three-dimensionally curved and slightly twisted in itself. To the right-hand side, you see this massive hockey stick and another component of the A-frame. And now we show you the crown. The crown we are milling out of a 400 millimeter thick steel block. And then it is completed by certain welded components. And after that, it is surface coated. You can imagine what a precision is necessary here to make all that working in the end together, all those components, especially since there is a very high tension inside that construction that needs to be controlled. We will come to that. So let's have a first look at the glass dimensioning. You saw it already in my first picture here. We have a nodal point here where two cables are crossing, the two cable directions are crossing. On top of that, we have a scissor fixing that is keeping four of the glasses in position. Inside the scissor fixing, there are small patches that provide a defined pressure point to the glass. We will come to that later also. Here on the right-hand side, you see a general model for the first assessments of fitting forces for the determination of joint deformations. So when we started in a very early step, we had to run different simulation to come up with the right glass type to be used in this construction. So for the three-dimensionally formed hull here of the glass, we were dividing the whole surface into three sections, section A, B, and C. in this case, mainly temperature differences that we have to consider in these three different sections. And on the right-hand side, you can see the end result of a relatively complex assessment that was running then, that for all these glasses, the recommended or the optimal glass would be a heat-strengthened glass. You see that here in that column on the curve facade. Heat strengthened would have been nice to use. However, we had a little problem there because we couldn't produce the glass in this three-dimensional shape as a heat-treated glass. So on the left-hand side, you see the glass build-up. It came out as a quadruple laminate glass 6886 build-up. And for the small front facade, which is not curved, which is covering the entrance area itself, on top, it is a triple glass with 12, 12, 12, all with SG foil in between. But how do we solve that little problem there with the technology in glass tempering here for this three-dimensionally curved glass? There was actually no real solution. We had to go for chemical tempering for that. So that's what we did. All the three-dimensionally shaped glasses are chemical tempered now. And you can see here in that little diagram on the bottom, chemical tempering has the disadvantage that the pressure stress in the glass is just about 30 micros deep. That's not a lot. So it meant for us that we have to be very careful along the installation, not to scratch the glass, in order to keep the structural integrity of the glass. So no scratches after installation. The problem is not there anymore because all the glasses are out of reach for anybody to scratch it. So here you can see some models of the glasses. You see that little point here. That point is that defined fixing point within the scissor fixing that I mentioned before. So here it looks as if it is a point fixing with a drill through, but it's not drilled through. It's just a patch that is inside the scissor fixing the glass. On top, you see the quadruple buildup of the glass. Here we were running all the necessary simulation, obviously, to make sure that it's structurally sound. But on the bottom, you see only 3 glasses. The reason for that is that for each and every single glass, we did another simulation where we took off once the top glass and in another one the bottom glass, and then run the whole exercise again to see whether the residual integrity is still there after the top or the bottom glass was breaking. So that's why we did the whole calculations again with only a triple build-up here instead of the quadruple build-up. So to be sure, even with 3 glasses, it works wonderfully. Here we have a quick look at the different load cases we were running, of course. Now we are running it for the whole glass panel with the quadruple build-up. We are running it for the whole hull itself, for the whole system. We are running it with the different dead load and live load requirements we are having there, and so on and so forth, to be sure that everything works nicely. And here we zoom into that thing a little bit. And now you see suddenly here we have no quadruple buildup anymore. We only show a single layer. So we run now all these calculations again for each and every single layer of each and every single glass. So in this case here, you see the top, the bottom layer of and the top surface. Now we are checking here the bottom layer of one of these glass build-up, the top surface, and see whether the glass stress is within the acceptable limits. Yeah. And again, we do that for each and every layer of each and every glass. So let's have a quick look at the testing. Here we are testing one of these quadruple build-up glasses. First, we are breaking it completely. It's a complete failure. And after the complete failure of the glass, or complete breakage, let's call it like that, that's better, we are testing the residual load capacity of the glass with a permanent load test. You see it's in a very conventional way done here, that we are loading the glass literally with weight and see what happens. Of course, it has to pass all the tests. Then on the right-hand side, you see another main test of a load test with a broken glass here. And as I mentioned, the glasses are anti-clastic curved panels, 2-directional settle. Here you see what we need to do to connect the steel components later on site. Now you remember the hockey sticks and the crown on top and so on. So how can we make sure that the connection forces here are exactly what we need? So what we did here, we were putting through here a tension rod with a thread. A rod is, it's a little bit more than a rod. It has quite a diameter, this thing. Then on the other side, we are attaching a hydraulic cylinder to it. We are extending that rod to the extension that it would have to provide the required force. So after it is expanded to that length with the hydraulic cylinder here, we are fixing that nut. And then after the nut is fixed, actually, we know exactly what is the force here in the connection point between these two steel components. Here you see now the test assembly we did in our steel workshop in the Czech Republic. All these things, these complex structures, we are test building first in our own facilities to make sure that everything works properly. So here you see the cable net while we just install it. And here on the right-hand side, you see then the already pre-stressed cable net. So what we are doing here, we have 3D laser trackers. All the cables are already marked with the positions of the cables by the cable company. But of course, these markings are not precise enough. So after we installed it and we start the stressing test or the tensioning test, then along these tests, we are pre-adjusting the positions of all those nodal points and marking them on the table, on the cables. So later in New York, when we install the whole thing, we can be totally sure that everything fits perfectly without needing to play around with the tension forces anymore. So here, that's an interesting thing. That's the look through the crown down, and the cables are tensed here. But what's really cool on this construction is that we have between the cable fixing point and the crown itself, we have a little sensor in each of these things. There's a sensor, and this sensor can tell us exactly what is the tension force in the cable. And these sensors are not only here now for the test build up in the Czech Republic, no, they are also there in New York, and they can be connected via internet to our headquarters in Germany, and we can read the actual tension force in the cable. This is especially interesting, for example, if there was an earthquake or a heavy storm or whatsoever, or massive temperature differences, we can monitor from Germany the tension forces in the cable, and we would know if anything is coming into a critical range, then we need to do something and we need to react. So the whole system can be permanently monitored from our headquarters in Germany. I will skip that little video now here because we also saw it in the teaser video, parts of it at least, and let's have a look at the installation here. That's the A-frame installation then in New York. You see the scaffolding and the cross beam here is installed. Then the crown is lifted to the top. It's a huge crown, as you can see here. It's a massive piece of steel. Then the cables are coming in. The cables are stressed. The glass is coming on top. And then this here is just the impression of after the installation of the last glass panel. And here we are installing, you remember in one of my earlier pictures I showed in the Czech Republic when they did these spandrel panels there. This is now installed below the horseshoe construction to close the whole construction there then to the ground floor. And then later they decided to laminate a New York City map onto these spandrel panels. So here you see the horseshoe. And then all around here, our 3D shaped steel panels, the spandrel panels, and then the lamination of the New York City map to it. So here we see the final result of the whole project. And you can imagine this point here is the structurally most challenging point, just to mention it, because here we go around the corner and all these cables are stressing the construction down. So let's have a quick look at the Moynihan train hall, also in New York. It's a grid shell construction. Totally, we have 5 shells here, 3 in this huge hall and 1 in a small hall. So here is an impression of the project itself. To the right-hand side, some impressions of the fabrication. I come to that. It's totally 5,116 square meters of freeform grid shell. We have 3,384 insulation glass units, including their aluminium framing. We have 670 tons of structural steel. A quick look into our fabrication again in the Czech Republic. On the left-hand side, you see one of the pre-prepared ladders as we will install them then on site. And on the right-hand side, it's the fabrication in Glasstech in Germany, where we do the aluminium works and the glazing of these aluminium elements. So they come ready glazed to site for installation. Here you see now how the glass is installed into that frames in our workshop. Right-hand side, you see the mass production of that. You see two of the letters going on their trip to the United States. And here the pre-assembled glass aluminium elements, and then we go for installation in New York, the scaffold and the propping. Here to the right in the center picture, you see how we start the installation of the ladders. On the right hand side, then you see the whole steel ladders mounted on the mid block, which is the single grid shell you just saw before in the overview. And then we start with the installation of the glazing. On the right-hand side, you see this ready-made, semi-unitized, you can call it aluminium frames with their glass in, how they are coming now into the frame. You can imagine there's no repetition in the whole project, so each and every part is unique, and logistics are not so simple to achieve all that, and everything fit perfectly at the first assembly already. And here you see in the steel also the integrated drainage system. So the system is drained between those aluminium units. Here is the ready-made, or the second line of defense is between the units. Here you see the ready-made construction. So let's have a quick look now in the technical background to it. So you can imagine these huge grid shells are not standing by themselves. So we had to use for each of these shells 3 spider cable elements to stabilize them. That's the red part you see in here. There's one at the rear, one in the center, one on the other side. Here you see 2 of the performance mock-up we were building up in Germany. It's a corner element here and the central part of it. And then we have a look now
Andreas,
into the... Yes?
We have 3 minutes left.
Okay.
I was informed that you would like to.
Yes, thank you. We have a look into the testing sequence here. I dropped that. So as you can see, we do extensive circuit thermal cycling tests, condensation tests. We had over 70 temperature and humidity temperature flow sensors installed inside this thing, 10 displacement transductors. We had to build a whole little building for it to have inside this part of the grid shell with the cooling aggregates here and so on and so forth. Here you see what happens there inside when we are cooling down. So we were running all these tests, of course, obviously all positive. And then after that, we come with the wind pressure test, air and water tightness, static air and water tightness dynamic. Here you see the propeller and the water system, the artificial rain system on it. And here we have the final result of it. And if you allow me, if we have enough time, we are just quickly running this small video here. That's a 2-minute thing. Here is the headquarters in Germany. A quick look into the engineering office there. And from the engineering office, you can look down into the fabrication directly. So of course, everything is 3D designed. Yeah, then we go down into the fabrication, all CNC, automized, still with a human touch, obviously. Then we have to mark all these elements with their individual numbers so we know where they belong to. Here, a view into the fabrication, pre-assembly, welding the alu frames. Gaskets coming in, glazing coming in. All high precision work. Ready-made products going out for shipment. Steelworks. First ladders after painting. Going into installation. and fixing and closing. And sealing. And so here you see it's not an even surface, it is kind of three-dimensional surface up there, faceted. And this is the final result. So I thank you everybody for your patience with me.
Do you have any experience with similar shape of canopy, but with double skin aluminum sheet cover instead of glass, and with maintenance openable in between also?
Yes and no. Yes, we have experience with shells that combine aluminium claddings and glass. Obviously, I'm not quite sure what is the reference to double skin now here. We did not yet do a real double skin grid shell, but of course the grid shells we are showing here are all insulated glass, but they are not what you would understand with a double skin. That you have an insulation glass plus another layer of glass in a certain distance to it. We didn't do that in glass. But in aluminium, of course, the panels we are using to close those shells have a certain build-up, but I would also not call them double skin in this sense. So I'm not totally sure whether this is answering your question, but a conventional double skin facade as a grid shell, we did not yet do.